In this section, I would like to discuss single displacement reactions and mention when such reactions are possible, and also redox reactions. Redox means reduction oxidation reactions. In this reaction between sodium and HCl, what you see is sodium is replacing hydrogen, and hydrogen is pushed out, and finally it makes H2 molecule. Nickel takes the place of hydrogen, and why the formula is NiCl2? Because nickel has oxidation number of +2. So when it combines with Cl-1, as we all know, this 2 goes down to the bottom of Cl, and 1 goes down to the bottom of nickel. So that's how you predict the product of the reaction. This reaction is possible only when nickel is more active than hydrogen. And there is a table, activity table, that I'm going to mention next, which tells you whether nickel is indeed more active. And indeed you'd find that nickel is more active than hydrogen. In other words, this kind of reaction can happen. If opposite was the case, if hydrogen were more active than nickel, that means nickel would not be able to replace hydrogen. In other words, this kind of reaction is not going to happen. This is the activity table, which your book has. The elements on the top, they're more active. Let me draw an arrow. So elements on the top are more active than elements toward the bottom. So let's now focus on nickel and hydrogen. Nickel is to the top of hydrogen. So nickel is more active than hydrogen. In other words, in a reaction, when you have both nickel and hydrogen, the nickel can replace hydrogen in a single displacement reaction. Now, here we're giving you a listing of acids. They all give H+ in water solution. Arrhenius's definition tells us that acid is a substance that gives H+ in aqueous solution. And these are the strong acids, hydrochloric, hydrobromic. So make sure you know these strong acids. Weak acids can give only smaller quantity of H+, because out of say 100, only 4 or 5 of them would break down, giving H+ ion, for which they are weaker acids. But all these acids you see here are strong acids. Now the definition of bases, according to Arrhenius's, bases are the substances that gives OH- in water solution. In other words, this kind of substances must have OH. And they're usually made up of group 1A and 2A hydroxides. So group 1A and 2A, and then you'd have hydroxides. Okay, now what is group 1A? Sodium plus is from group 1A, and OH-, when they combine, they're going to give you a strong base. NaOH is a strong base. Similarly, calcium, which is +2, when it combines with OH-, keep in mind it's minus means -1, so that 2 goes underneath OH, so the formula is CaOH2. So these are all strong bases. They would break down 100% in water, giving OH- in water solution. Now, that's Arrhenius's definition. Bronsted-Lowry's definition is slightly different. According to Bronsted-Lowry definition, a base is proton acceptor. Proton means H+ acceptor, just like acid is H+ donor. Now, how does it accept H+? If I have OH-, OH- will be attracted to H+, because they can combine and make H2O. So either ways, you'd find that OH- would be a base. Now we are going to discuss about oxidation reduction reactions. First, let me define what is oxidation. An oxidation happens when an atom or ion loses electrons. So loss of electron is oxidation process. On the other hand, gain of electrons is a reduction process. And we're going to define what is called oxidation number. And in case of oxidation, oxidation number increases. In case of reduction, oxidation number decreases. And both reactions happen simultaneously. Now here we're going to mention about oxidation numbers for pure elements. Keep that in mind. For pure elements in the form of element have an oxidation number of 0. For example, if I have H2 molecule and that's oxidation number is 0. Similarly, if I write down oxygen, that also would have oxidation number 0. If I have an ionic substance, for example, in a solution I have Cl minus, that has oxidation number of -1. Now, if there's anything that we know so that we can quickly say what kind of oxidation number you'd have in a compound, yes. If it's a group 1A, let me write down this. In general, in many cases, this is going to work. Group 1A, those elements are +1, 2A. Even though I mentioned these when I discussed about formulas, but those pluses are nothing but oxidation numbers, 3A plus 3. And then leave out 4, because 4 can have more than one oxidation numbers. 5A, you subtract 8 from 5, from the group number. So it would be -3. 6A would have -2. 7A would have -1. So by subtracting 8 from group numbers. So that's how we get oxidation numbers when they make a compound. As an example, say calcium makes a compound with Cl. Calcium is from group 2A, having +2. And that's the oxidation number on calcium would be +2. When it makes a compound with Cl -1, the formula would be CaCl2, calcium chloride. In other words, if I give you calcium chloride, you can quickly tell that what oxidation number calcium has. Calcium would be +2, and that 2 went down to the bottom of Cl. So that's how we can find out. If you trace backward, calcium would be +2, Cl is -1. Now here we're showing you a reaction between magnesium and oxygen that gives magnesium oxide. Magnesium is a pure element on the reactant side, so its oxidation number is 0. O2 is a pure element, oxidation number is 0. But whenever it makes magnesium oxide, it's no longer 0. Magnesium is +2 in this compound. It's coming from group 2A. Oxygen is coming from group 6A, which is -2. And +2 -2, that makes it neutral, so it checks out. So what you see here is magnesium starting with 0. As a result of reaction, its oxidation number has increased to +2, and that's oxidation process. On the other hand, oxygen, O2, begins with 0 oxidation number, and that decreases to -2. So oxidation number is decreased, and it's a reduction process. Now, we can go over a problem which is number 51b. So let's see what we have in 51b. A reaction is given, and you need to find out which element is oxidized and which element is reduced. So let me first write down the reaction. 3 ferric nitrate. So let's write down here 3 FeNO3. Keep in mind there are ferrous nitrate as well as ferric nitrate. In this case, they give you ferric nitrate, so there'll be 2 there. I'm going to ignore the state of matter. In other words, I'm not going to write down aqueous or solid, because for this answer, it doesn't matter. Plus, this is 51b, plus 2Al. that's solid, giving 3Fe plus 2 aluminum nitrate, 2 aluminum nitrate, NO3. Now keep in mind aluminum is plus 3, so it has to be 3 here. Okay, let me double check whether I copied my question right. 3 FeNO3, 2. That's ferrous nitrate, not ferric nitrate, so I was wrong because this is plus 2. 2Al, 3 Fe, and 2Al NO3, 3. Okay, now the question is, you need to identify which of these elements have oxidized and which one have reduced. Now these are compounds. Let's now analyze the compounds on the reactant side before we find out what kind of change had happened. FeNO3, 3. Of course, Fe would be plus 2. And NO3 would be minus 1. You can always double check. When Fe plus 2 and NO3 minus 1 reacts, it gives you FeNO3, 2, because 2 goes down NO3. Here we have aluminum, which, as it is, I'm just writing out like this. So here oxidation number on Fe2 plus is plus 2. And NO3, that's, of course, I mean, this whole thing is minus 1. That's net oxidation number. Fe is 0. It's a pure element. Aluminum is 0. It's a pure element. Now we're looking at AlNO3, 3, where Al is plus 3 and NO3 is minus 1. Now keep in mind, this should be a balanced reaction. I have 6 NO3 on the left hand side, 6 NO3 on the right side. So nothing had happened to NO3 minus. So that's, you don't need to worry about it. So now we need to deal with only Fe and Al. Fe2 plus started with plus 2 and ended up with 0. That's a decrease. So decrease in oxidation number means reduction. So Fe2 plus has undergone reduction process. On the other hand, aluminum started with 0 and became Al plus 3. That's an increase in oxidation number from 0 to plus 3. So let's write down here plus 3. And that's oxidation. And this kind of change would happen simultaneously. That means you cannot just have reduction happening and no oxidation happening. So actually both would happen simultaneously. So answer to this question is Fe2 plus has undergone reduction reaction and aluminum has undergone oxidation reaction to Al plus 3.